He did get the part about the charge. Yeah. Anyways, there was a joke at the bottom. There goes again.
You haven't seen our new logo? Yeah. Okay, everyone, it's a pleasure for me to announce our speaker today, Dr. Nader Haghighipour. You may notice by looking at his apparel today that you can either call him an Iranian Hawaiian or a Hawaiian Iranian, depending on what day of the week it is. Nader has 3 degrees in physics, first one from the University of Tehran, next 2 his master's and Ph.D. from the University of Missouri-Columboa, where he did work in both cosmology and planetary dynamics. After he graduated, he went to UC Irvine for a year or so, where he's pretty strong in high energy astrophysics and other things like that. And then he went to Northwestern, I think to be with Fred Razio for a little bit. And I guess Chicago was too cold and windy for him, so he applied for a job here with me. And in 2001, he came to DT and worked with me on an Origins grant, and then he graduated to become an astrobiology fellow, which has worked out pretty well for him, because he's now the head of the IAU division, newly formed Division F on planetary science and astrobiology. So he is the world's leading astrobiologist right now. But after he left us in 2004, he went to the University of Hawaii, I think to work in part with the astrobiology group there. They have an astrobiology node at the time, Karen Leach and all those folks. He's been there ever since. They've not been able to get rid of him as far as I know so far. So anyway, he's passing through town, doing things like reviewing proposals and things. Maybe one of mine, I don't know. We'll see. He can't say anything about that. And today he's going to tell us about some exciting stuff about what Kepler has been finding for planets around binary stars, and perhaps a little bit of theoretical emphasis.
Sure.
Because he actually put together a whole book on planet formation around binary stars before they really knew about any planets around binary stars or thereabouts. So, Nader, tell you so much.
Thanks so much, Alan. It's great to be here. It's great to be back. Yes, as Alan mentioned, it was 15 years ago that I was a postdoc here. And believe it or not, when I wrote my job application for Alan's postdoc position, I wrote in there that I would like to work on planets in binaries. We ended up working on formation of Jupiter and with George Weatherall on terrestrial planet formation. But that work, Planet in Binaries, started in my last year of graduate school, and it continued here, and I will show that Alan also contributed to that as well, and the seeds were actually planted here, and then when I went to Hawaii, I started working on it, and it became a field by itself. So what I'm going to tell you is about the new discoveries that we have made using data from Kepler telescope, specifically finding circumbinary planets. And I tell you about the current state of research, the discoveries, the theoretical implications, and how we explain the results and where we are going. So let's start from here. When you hear the planets in multiple star systems, in binary systems, immediately 2 things comes to mind. These planets can have 2 types of orbits. The planet can go around one of the stars, and the 2 stars rotate around their center of mass, or the 2 stars can be close to each other, and the planet goes around both of them. The idea of planets in multiple star systems and all that existed for many years. I will show you some references going back to the 70s. So this is not something new. In the 80s, early 80s, and late 70s, this gentleman, Rudolf Dvorak, in Austria, in Vienna, studied these and their dynamics in details, and at that time he came up with this terminology. He called the system where the planet goes around the primary S-type, standing for satellite type, and the system where the planet goes around the entire system, P-type of planetary time. The reason was that he was interested in studying Trojan asteroids. So for him, this was Jupiter, this was Trojan asteroid, and that was Sun, and he was trying to study that, called it satellite type. And then at the same time, he tried to extend his work to other cases as well. Terms stuck, S-type and P-type stuck, and now in literature, people use that when they say P-type, they refer to circumbinary planets. When they say S-type, they refer to circumstellar planets in binaries. And so throughout this talk, when I say P-type, I'm referring to that, and when I say S-type, I'm referring to that. The whole story of this planets in binary system started with the first discovery in this case, And that is what the that's where the difficulty is. That is where theories still, after about 20 years, can't explain formation of planets in those systems. And then it was implications of those results that planets should exist in circumbinary orbits as well. And as Alan mentioned in our books, we explained how you find these planets, and I will show you a couple of papers. We made some predictions, and lo and behold, in 2011, we found the first one, and the rest of the story. So this is just to get you oriented that what orbit is which, and now I'm going to go through the history of the planets in binaries and give you a little bit of flavor of what people were doing in the past and how it resulted to the current state. And then I'll show you some current results. So as I said, the story goes back to 70s or so, and these are some old references. I just want to show this just to show the dates that the study of planets in binaries goes way back. Most of these people studied cases that did not exist, or they studied planets in binary systems around binaries in a hypothetical case with applications to, say, artificial satellites going around Earth or Trojan asteroids, things of that sort. But the reason that the idea of planets in binaries didn't pick up and stayed at the level of working on computer was because of this. This is, look at that, this is in a book that Bill Hartman published in 1999. And even until that time, the idea was that depending on how the molecular cloud rotates, how fast it rotates and collapses, you will either get a planetary system or you will get two cores, and you will never get a planetary system in or around binary stuff. Well, we know that this is, now we know that this is incorrect, but this was supported by several subsequent computational simulations as well. The idea behind this was so strong that later discoveries were totally affected by this mentality that you can't have planets in or around binaries. In 1988, Bruce Campbell and Walker Yang, Gordon Walker was the leader of the group. They were trying to find planets, extrasolar planets, and they were studying a bunch of targets. One of the targets was Gamma Cephei, which is the primary of a binary system that has a separation of about 21 AU. So they measured the radial velocity, and they say that there is a probable third body variation of 25 meters per second amplitude, 2.7 years, and they said that this could be a planet around one of the stars of that binary. Remember, the binary is 21 AU apart, and they were saying that there is a planet around one of them. So they published this, but then what is interesting is that this idea that you can have planets in binaries was so strong that they themselves doubted their discoveries. And then later on they come and say, probably that's just chromospheric activity of the star, and no, it cannot be. And then they basically disputed their own discovery. In 1992 they published a paper that said that no, forget about what they said. I will show you that discovery was correct, and if they had stuck with it, they had discovered the first extrasolar planet in 1988 in a binary system, and that just imagine how that would change our mentality. But I want to tell you that how strongly this theoretical work affected the discoveries and observation at that time. One thing that contributed to this wrong impression was a work that was published in 1994 by Pavel Artemovich and Lubo. This was part of Pavel's thesis. What he showed was that if you take two cores and put them at different distances and put disks around them, these are disks of test particles, and let the cores interact with one another, and the perturbation of one core on the disk and on the other one truncates the disk. And then he argued that the truncation is so large that the disk will lose material, and it will not have enough material to form planets. This is for disk around two stars that they go around each other, the S-type system, and this is for the circumbinary disk. And he showed that there will be so much perturbation that you don't get planet forming in these systems. Well, again, we know that this is incorrect, and that simulations are good, but the implications are not valid. It was until 1988 that Rodriguez et al. Published a paper on the discovery of L1555 and this is a binary with 40 AU separation, the size of the solar system. It has disks around both components. Each disk is about 10 AU, and they have this about 5 times more massive than minimum mass solar wind. So when this came out, I started working on planets in binaries a year before that. And when this came out, then many of us, including Alan, we were thinking, oh, if this exists, planets could form around the stars of a binary and in circumbinary as well. And we started pushing observers to go after it. This is a work that Alan published in 1998, putting solar system on that system and showing that it is possible to actually form planets within the disk of that system. And this was another discovery in 1998 showing that, oh yes, you can have a disk around one of the components of the star. So all this pointed to the possibility of forming planets around the star of the binary and with extension in circumbinary orbit. So we started pushing observers, and in 1999, this paper came out. This is October 99. In a letter to Nature, this paper came out. So Dave Bennett announced the discovery of the first circumbinary planet with microlens. So they say that, I don't know if you can read it from back, this is the Macho project, Macho 97 BLG41, and that was the star that is a planet that goes around in circumbinary orbits. It goes around 2 stars of M and K dwarf and M dwarf, and the separation is about 7 AU and all that. This was very nice, and when it came out, I remember I first heard about it on CNN. I didn't actually see this, and then I went and found the paper and started working on it. It got my attention because at that time I was thinking, okay, so it was discovered that shows that planet can form in those systems. Let's go study the dynamics and all that. This is just a discovery. If you are unfamiliar with the way that microlensing works, you have your lens that when the planet goes around the star, it creates a second lens, and you see a blip in the light curve, and that blip is right there indicating that there must be a planet. So this was all good, but then people immediately poured on it. Science wrote an article on that, and a report on that, and in that report, this report continues all the way down, so this is the continuation of that. There are quotes by Matt Holman and Jeff Marcy. Matt says that, if you read this area, Matt says that the orbit is unstable, and the planet cannot exist because it is sitting right where the region the planet becomes unstable. 2 things caught my attention in this letter. These are all back in 1999. One thing is here, the planet is far enough away that it should feel the 2 stars as if they were one. Keep this in mind when I talk about planet formation in circumbinary disk. I get back to this. This is a very important point. The other thing that caught my attention was that at the same time, a competing group, Planet, was also looking into this system, and they weren't able to confirm that. So what happened after that was that the planet was disputed, and I learned that hard way. I wrote a proposal, and it came back said that your planet doesn't exist. So here you go. So anyhow, this gave us some motivation, although it disappeared. It gave us some motivation that if you push hard, you may be able to get something. One thing that I want to mention here is that about the stability. The reason that they were saying that planet is unstable is the following. If you look at these two, if you take these 2 configurations and take your 2 stars and distribute test particles around them and study their interaction with the star, you will see that some of the test particles become unstable, go away, and some of them stay. You can actually do this, if you do this many times, you can come up with some empirical formula. In 1988, same person, Dvorak, formulated these stabilities and showed that there are some outer and inner regions to the stable and unstable areas that relate to the eccentricity of the system and also its mass ratio. That work was a little bit too simple. So in 1999, Holman and Wiegert published a paper and extended that to many more cases and bigger parameter space, larger region of the parameter space, and they showed the following. Let me go back to this simulations. What that stability shows you is the following. You see, if you look at these regions, if you are too close to the star, you become unstable because of the interaction with the star. If you are close to this one, you become unstable as well. So, but there is a region in here that you stay stable. And that is where you can get that region, the inner and outer boundary of that region, related to the eccentricity of the system and also its mass ratio. The same for circumbinary planet. In 1999, Holman and Wiegert formulated this and showed that the inner and outer boundaries are how they relate to the mass ratio of the binary and the eccentricity. And the same for the circumbinary. I'm going to use this quite a lot to explain that there is an inner region, and we call that the outer region of the stability. Any planet that comes interior to that, because of the perturbation with the binary, will be unstable, while things that are far away, they stay stable. Now, remember that highlight the thing that I said. I will get back to it. If you go far away from here, you're stable, and if you're standing here, you really don't care if that is a binary or that is a single star. And there's physics behind that that connects to the formation as well. So I'll get back to it, but keep that in mind. That's what they were saying, and that is the formula they talked about. Okay, so this all happened within that time frame, but we kept pushing observers to look into it. Many observers did not want to look into planets in binaries, but Artie Hattis did. He went back to that gamma Ceph system and observed it for more years, and then put all the data, observational data from distant telescopes together. This is from Ph.D. There are McDonald's and McDonald's and McDonald's. And then put about 50 years worth of observation together and showed that if you go back from 1988 to 2003 and put all these radial velocities together, they actually stay, they don't go away, and they truly point to an actual planet existing there. And that was the discovery of the first planet in a binary star system. It's a Jovian type planet, 1.67 Jupiter mass, Semimajor X 2.1 AU, eccentricity of 0.12. This is a cartoon of the system. You're looking at it from above. The planet goes around the primary star. The separation is about 21 AU, and the eccentricity of the binary is about 0.21. Once this was announced, then a new chapter in the whole field opened up, and many of us, including John, started looking into the viability of these type of scenarios, whether we can form this type of planets, and where they could form, whether they could be stables, and many other things. Last night I put about 6 slides together to tell you that what are the problems with this S-type systems, and where we stand as far as understanding the formation and evolution of this system. And then when I finished, I realized that, if I go through those, I will not be able to finish my talk. So if you're interested, ask me. I'll quickly go through it after my talk. But I'm going to stop here and focus on circumbinary planets, and I'm going to start it from there. So in 2005 and 2003 and 2005, more evidence appeared, observational evidence that planets can form in circumbinary disk. And this is a triple star system with disk around one component, and then GG tau with a disk around both components, suggesting that planet formation can proceed within the star of a multiple star system or circumbinaries. I'm going to use this and switch gears to circumbinaries and explain to you how we use Kepler data to find circumbinary planets. Prior to Kepler, Alan contributed to that book that I wrote. John contributed to the book that I wrote. We came up with this idea that the planet formation in circumbinary orbits could be efficient, and you could have planets. And then in the book, in the chapter, I explained that how you can find that if the planet through astrometry, radial velocity, transit time variation, and also through transit. In the 2010, this paper came out by our colleagues in Poland, and they suggested that Kepler, they referred to all those methods, and they said, taking all those methods in that book, Kepler will not be able to find the circumbinary planets. And they had their own arguments that the Kepler sensitivity is not good enough and everything. So in 2011, we published a paper and disputed what they said, and we showed in this paper that you can find it, and you can find it through transit photometry, and you can find it through transit timing variations. And we put the region of the primary space that is more promising to find these planets, and we explained how you do it through the transit time variation and transit photometry and all that. And this came out in January 2011, and the first planet was discovered in, it was announced in August of 2011. The way that we find planets is the following. I'm going to show you a movie. This is an artistic rendering of Kepler 47 with 2 planets. These are circumbinary planets. This is your system, the 2 stars, 1 planet here, 1 planet here. You see how these planets go around and everything, and then I'm going to use frames of this to show you how we find these planets through transit photometry, and then we'll take it from there. So, okay, here. Whoa. What happened? Oh, there we go. This is, I think that's it. No? I think that's it. Yes. Okay. Planets go around the star, but the important thing is here. This is one of them, the smaller one. Okay, pay attention here. 2 stars eclipsing each other, and planet goes around one and the other one. Okay, and that's how we find them. So here, let's go back here and I'll show you the frames. So this was the movie, and this is one of the frames. This is one of the planets, right? And the 2 stars. So what happens is that when we observe this, we observe the eclipsing of the star when the secondary goes in front of the primary. We observe that, and then the secondary goes behind the primary. We observe that as well, and then the planet goes in front of the primary. We observe that too. And watch this. The planet goes in front of the secondary as well. We observe that too, and then that. Okay. And then when you put all that together, it becomes something like this. You have the eclipse of the secondary going in front of the primary. You have the eclipse of the primary going in front of the secondary. And then you have this small little blips here when the planet eclipses the secondary or the primary. The first discovery was done by going through 1,000 light curves by eye and try to find those little dips that keep repeated. It took about a year for Lawrence Doyle to do that, but it came up. Well, we finally were able to detect Kepler 16, and that was the way that the first circumbinary planet was detected. This little thing, that yellow one, when the planet goes in front of the primary, and the red one when the planet goes in front of the secondary. This is a cartoon of the system, and this is the artistic rendering showing that the planet transits both the stars. This is the actual data for secondary going in front of the primary, and primary going in front of the secondary, planet going in front of the primary, and planet going in front of the secondary. And just look at the variations and the depth of the dip, and you see how difficult it is to find these planets, and that's why it took him about a year to find all this. Okay, so this was detected, and then we realized that the planet is in the habitable zone. Calculating the habitable zone of multiple star system is an entire industry by itself. It's very different from calculating habitable zone around single stars. So Lisa Kaltenegger and I developed the methodology for it in 2013, and we noticed that Kepler 16 is actually in the habitable zone. What you see here is extended habitable zone, optimistic habitable zone, and conservative habitable zone. And the binary is there. The planet, the red one is the boundary of stability, and the planet is very close to the boundary of stability right in the habitable zone. The planet itself is Saturn size, is slightly bigger than Saturn, so it can be habitable. When we discover this planet and the habitable zone, we write in the paper the planet cannot be habitable, but it may have moons that could be habitable. So just keep that in mind. I have a student currently working on detecting moons of circumbinary planets, but I'm not going to talk about that. Okay, so say again.
What's the spectral type of the primary?
The primary is a K. The primary is a K,
okay.
And the secondary is an N.
Okay. Thank you.
One interesting thing, when we discovered this planet, we noticed something very interesting. Remember that the simulations by Lubo that I showed, and I showed the boundary of stability. So when this planet was announced, this thing came out. This is the boundary of stability that I mentioned, and we noticed that the orbit of the planet is very close to the boundary of stability. So that caught attention of a lot of theorists. They were saying that we theorists like to work with only one sample. So. Solar system, right? How many years we worked with solar system? So this came out, and everybody poured on this. They're trying to explain how this planet can form right close to the boundary of stability and all that good stuff. I'll explain to you. They didn't succeed, but there's a reason behind it. So they were saying that let's go identify all these eclipsing binaries, determine where the boundary of stability, and look for planets in that area and everything. That didn't work out either. But this caught attention of the theorists, and they were trying to explain how this happened. So a lot of people, all those people, try to form, I'm just using this as a cartoon, try to form Kepler 16 around the boundary of stability, right? And none of them work. There is a reason behind it. The reason is the following. I'm going to show you a simulation similar to Lubo, and then you see specific things happening to the disk that prevents planet formation. This is your binary. You're looking from above. You have a bunch of test particles. I specifically put Earth-like planets here, not interacting with each other. So something like about 10,000 Earth-like planets, Earth mass planets, and they're not interacting with each other. Now I'm going to turn the disk edge on, and I'm going to run this to see what happens to the disk. So when you turn the disk edge on, I'm going to also show these resonances corresponding to resonances like 5 to 1, 6 to 1, 7 to 1, n to 1 resonances with the binary. So 5 to 1 means a planet here is the period ratio to the period of binary is 5 to 1. So look at that number up there. That is the time of the simulation. So you see this, what happened? So another snapshot. You see what's happening? Another snapshot. So it's not, starting from here, these resonances basically cleared out their surrounding and caused the particles or planets to gain high eccentricity. The reason those people weren't able to form planets in the vicinity of this stable region is because these resonances, they're right at that stable region. They're very close to the stable region. If you put planetary embryos or planetesimals there, because of the interaction with resonances, the eccentricity become high, they hit each other, they shatter each other instead of forming planets. So if that is basically what you see. This was known in the work of Holman and Wigan in 1999, but unfortunately, those who were more trying to form those planets didn't pay attention to it. And what is interesting is that this is another way of showing those resonances. I'll explain to you what the colors mean. What is interesting is that these planets that we have found, all of them are stuck between these major resonances. And again, there is a reason for that. What I'm showing here is similar to that test particle thing that I showed you, but instead of using the actual orbital dynamics of the planet, I'm using something that is called MAGNO, mean exponential growth factor of nearby orbit. Forget about these fancy things. All it means is that you look at the planet orbit for about, say, 10,000 years, and then you see which direction it goes, and based on that, you make a judgment whether it is unstable or it could be stable. And this is where Kepler 16 is, between these resonances. These are the resonances that show you that those resonances with the binary that could be unstable. As I'll show you a few more of these so you see that all these planets that we find, they're all between resonances. Okay, so if you can't form the planet here, but the planet is close to this orbit, to this location, what does that mean? Probably planet formed farther out, migrated, and then stopped at the place that was close to boundary stability. In other words, the boundary stability doesn't have any significance. It is the planet-disk interaction. And the planet must form farther out because close to the binary, the perturbation with the binary doesn't allow for the planets to form, right? So planet has to form farther back. This goes back to the first couple of slides that I showed. The planet, if it's far away, it doesn't feel the binary. The planet has to form farther back. Similar to the formation of planets around single stars. Take any scenario that you want. That is not important. The important thing is that when you're back here, you basically don't see there are two stars and you don't feel the perturbation as much as when you are close. a planet formed there, interacts with the disk, and if it manages to stop, it will definitely stop between resonances. It has no choice, right? And I will show you that most of the time it doesn't stop, it just plunges into the binary. This is what I just explained. You have the planet farther away, and the planet must migrate, and so it's just what I just explained. Must migrate, and as it comes close to the binary, is dynamic, is governed by the interaction with the N1 resonances. Okay, so this is all good, keep that in mind. I'll get back to it when it comes to planet migration and formation, and I will explain to you how this migration happens and what should be the properties of the disk. This is the current state of circumbinary planets discovered with Kepler. These are 6 of them. These are another 3, and there are 10 systems and 13. There are 9 systems and 11 planets. We have many more in the back that we are working on, and we're hoping that within the next couple of years, by the time that data from tests become available, we'll be able to publish those. Our strategy is to, because these are really hard to find and to bet, our strategy is to put a self-imposed deadline, and those are usually conferences. So our goal is the Aspen conference. There's going to be a conference next year in Aspen in March, and on dynamics of exoplanets, and our goal is to announce one more over there. So if you are interested, come to Aspen.
So lowercase b is the designation for the planet?
Yes, and this is the gentleman who did that is sitting all the way back there, and that's his fault.
Why b and not a? I don't understand.
Should I answer or A? Okay, A is the star. So when he was putting that,
The stars are uppercase A.
no, listen. When he was putting the when Paul and Jeff were simulating these RVs in the code, they were saying object A, object B, object C. So A was the star. And in circumbinary cases, in planets in binaries, we took that, and although for binary cases A and B are capital, we start with letter B, indicating the first planet discovered, and we just go that way. Okay, so I just mentioned that this Kepler 16 was close to boundary stability. This tells you the location of the currently known circumbinary planet with respect to their own boundary of stability. This has been so what I'm showing here is the binaries. You're seeing it from above. These are the binaries, and you only see the secondaries. And the boundary of stability has been scaled to the separation of the binary, so we can put all of them on same graph. You can look at this from this way, and that may be a little bit better to indicate that not all of them are close. Some are farther away, and the most recent one that we announced is way far back. But there is some sort of accumulation, but this accumulation really has nothing to do with the boundary of stability. It has to do with the way that the disk behaves close to the binary. Just to show you another example, a few examples of these planets migrating and getting captured into between resonances. This was Kepler 16, this is Kepler 453b, and just so you know that we test this with different methods. This is another method we are using, maximum eccentricity criterion, and this is Kepler 34, and they all, if you look at them, they are all stuck between resonances. Okay, so how do these planets form? We believe that they form similar to planet formation on single stars farther away, where the disk doesn't care, it has a binary at the center, and then it migrates. So let me explain the migration and the way that we developed the theory for the migration and all the obstacles we went through until we got a handle that what should be the properties of the disk. We started with a locally isothermal model, and we took our disk and we let the disk evolve and cool down, not cool down, evolve and dynamically calm down. And then we put a planet in it, and we let the planet interact with the disk. We put the planet farther back, the way that the disk interacts with the binary and all that. That has been done. Let me show you. I will go through the slides, and then I'll show you some of the animation, so it shows what I'm talking about. I will show you. Yeah. Well, what happened? Okay. So I will show this. Oh, there you go. It's working. So we let the disk dynamically come down, and then after it's all settled, then we put the planet farther back and we let it interact with the disk. So again, the disk is isothermal. We put the planet all the way back here. We took the Kepler 38 for a reason. Kepler 38 binary is eccentric, and the planet is binary is circular, and the planet also has low eccentricity. So we wanted to eliminate the effect of eccentricity, just focus on planet migration. We took that system. I'll show you Kepler 34, which both planet and the binary are eccentric, and I'll show you what comes out of it. We put the planet all the way down there, and we let it interact with the disk, and these are the times and the snapshots, and the planet comes here, but then we noticed something interesting. Oh, it actually works, great. So we noticed that when we let the migration happen, this is the boundary of stability related to the binary. The planet comes and actually penetrates interior to the boundary of stability, where it becomes unstable, and actually becomes unstable. After a while, the planet goes away. So we noticed that the locally isothermal disk may not be the appropriate way to go. We have to include the radiation, and we have to take the disk to be radiated. This is the way that we implemented the radiation in the disk. And I'll let you go through it. I'm not going to explain what this is. These are all very well established methods of making sure how the radiation is distributed in the disk, how the disk cools off, how the radiation interacts with the planet, and the planet cools off, and all that. And then we did a similar experiment. We put the planet farther away, and we let the whole thing happen. And let's see it. Oh yeah, perfect. So the planet migrated, and this time came very close to the binary stability and just settled right there. That told us, remember, we really don't know what was the original disk of Kepler 38b, but it told us one thing, that if you want to do this right, your disk has to be fully radiative. Your interaction has to be with a disk that includes all that physics, and locally isothermal is not going to do it for you.
Nader, what's the mass of the planet?
It's about half of, no, it's about half of Saturn. Yeah. We did similar experiment in a later paper with Kepler 34. This time, binary and planet are eccentric. And this just tells you where the planet is. And again, we let the disk calm down, put the planet in there, and we let the system go through. And what we notice is that, well, as it's going, let me explain one thing. This region that is white is the region around the binary that we do not simulate, because if we get close to that, the approximations we put in our code will break down. And that stays. However, we allow the gas and the binary to interact with one another, so there is flow of gas to the binary. And there is and then to make sure that the density stays constant, we introduce gas at the end of the farther away at the end of the disk. We introduce gas to it, so the density stays the same. There is no closed boundary here. Some simulations take that region and put a closed boundary, and they don't let the binary and gas to interact with one another. If you do that, you're artificially creating a barrier, and that will give you unreliable results. This hole that you see here is because the binary is eccentric, and when it interacts with the disk, it creates a hole in that region. The planet can penetrate into that hole because that is not the region of stability. The region of stability that comes from celestial mechanics may actually be inside that hole. So when we saw this, we realized that, oh, our planet is far away from where it's supposed to be. The orbit is about, you see the difference. The difference in reality is about 15%, and we get it to be about 30%. So we noticed that somehow this planet has to come closer, although the interaction with the disk puts it in a nice stable orbit and all. So we predicted that Kepler 34 must have a second planet that interacted with this planet, pushed this into closer orbit, and that planet itself went into a non-transiting orbit. And if you have a planet in non-transiting orbit, then it has to, if it's close enough, it will apply some sort of perturbation to the system or to this planet, and you should see its effect in the transit and transit timing of the planet. So we do see the effects, but the effects are too minuscule, and unfortunately I don't have it here. So the prediction was that there's a second planet here is non-transiting, and it induces transit timing variations. We do see the transit timing variations, but they're so small that we can't reliably model that. But that tells us some other story, that there may be planets that are not transiting, and how can you find the circumbinary planets that are not transiting? And that's the story I'm going to tell you. So before I get to that, as we were finding these planets, trying to explain the formation and everything, we came across this system. I showed you Kepler 47. What was interesting about this was the light curve. What I'm showing here is transit of planets in front of the primary star. I have one slide for transit of planets around the secondary star. The colors correspond to different quarters of the data coming from Kepler. So these are all basically the same star. And we were able to find the transits that occur in front of the primary, and we were able to find transits that occur in front of the secondary. And when we modeled that, we noticed that we can only model these if we have two planets. Well, that is something that the theory of planet formation, especially from Kepler 16, was telling us. If these planets form farther out and similar to planet formation on single stars, this produce multiple planets. So there's no reason not to have multiple planets in circumbinary orbits, and this confirmed it. There is a more interesting story to this, but then when this came out, this was the confirmation that multiple planets can also exist in circumbinary orbit. In other words, planet formation in circumbinary disks is efficient and can produce multiple planets. Now, what is interesting, there are two interesting things about this. I'm going to explain that a little later. Another system that we started working on, I'm not going to put its name up there yet, but just hold on for 2 slides, was this system. We detected about 2,000 eclipsing binaries, and we were monitoring them for the signs of planets. And we had this system, and for quite a while, what you see here is the actual time. For quite a while, we didn't find anything with it, and then later quarters of Kepler show transits of the binary. This is eclipsing binary. I'm sorry, the transit of the primary. This is eclipsing binary, and except for if you take the binary and secondary going in front of each other, and you take that away from the light curve, you don't see anything. It was just flat. And then we saw that in addition to those, when you remove the eclipsing of the secondary and primary by themselves, then you see that the primary gets eclipsed by some object. You see, we saw this. Those of you working on transit know that we only need transits to come up with the orbit of a transiting object. So we have three, and then we try to model that, and the model told us something very interesting. So this is the binary that you're looking from above, and there is a planet that goes around and eclipses the primary star. We noticed that the planet is, so this is the primary, and this is the secondary down here, the planet going around the whole system and eclipses the primary. We noticed that the orbit of the planet has about 2 degrees inclination with respect to the plane of the binary. And that 2-degree inclination causes, because of the interaction between the planet and the binary, the orbit of the planet wobbles, right, by about 2.5 degrees, 2 degrees. Sometimes the planet transits, sometimes it doesn't, right? So this is how we show that. The wobbling of the orbit, and the secondary is here, the primary is here, and this is the blue is the orbit of the planet. Sometimes it transits, sometimes it doesn't. And this tells you what should be the impact parameters for the primary, for the planet to transit, and that tells you the time of operation of Kepler. Okay, so if Kepler had been launched and operated, say for instance here or here, we would never see that, right? Now, what does it tell us? It tells us that there must be many of these non-transiting circumbinary planets that we are not able to find, and if or we could have found if the Kepler had instead of 3.5 years had been 4 years, 5 years, 6 years, right? So the bottom line here is that there must be many. This planet, the probability of transit is only 8%. There are 92% more planets out there that are not transiting, and that tells you how efficient planet formation is circumbinary disk star. This is the planet that is discovered. The mass of the stars, the mass of the size of the planet is mass. We get the mass of the planet from eclipse and transit time variations, and the inclination of 2.3 degrees. After 453, we also have 413 and 453. They are both inclined. Going back to Kepler 47, I showed you the eclipse of the primary, and when we announced that in the discovery paper in Nature, we also mentioned that there is one transit that we cannot explain. And at that time we were thinking this transit could be another planet, but we didn't have an evidence for it. So we just left it over there. We called it extra transit. In the paper we call it an orphan transit because we don't have an explanation for it. This is something very interesting happened. So this is that orphan transit, right? The transit was detected in 2012. As we were observing and monitoring this system in 2013, and so we got more, as the more quarter data came from Kepler, we got more information about that. And then we noticed that when we went back and studied the light curve of the primary, we noticed that that transit appears 186, 187 days later, appears right there. Right. So we were thinking, okay, if this is a planet, did this transit exist 187 days prior to that? Of course. So we went back to our data and we found that, right? How about before that? Yes. How about before that? Yes. And then we waited for the next quarter and there. Now, see, so the planet is real. We were able to find the third planet. But what I want you to see is the depth. You see the trend? Becoming bigger and bigger and bigger. What does it tell you? The planet is inclined, right? So it wobbles, orbit wobbles. Sometimes it transits, sometimes it doesn't. And
So
as
some
it,
of those are secondary transits. They are partial transits.
it could be, yeah. But the point is that as the transit depth becomes bigger and bigger, it means that the planet comes more and more closer, covers more of the disk of the star. So the current state of Kepler 47 is that it has 3 planets. We were able to refine the masses as well. Now I'm going to show you the other thing about this planet. Look at the primary. Primary is a sun-sized star, right? Look at planet C. It's a 300-day orbit, right? And look at this mass. It's a super Earth in almost 1 AU from a sun-like star. This is the state of the habitable zone and the planets. The planet C is right in the middle of the conservative habitable zone. The reason that you see the habitable zone is going back and forth is because the radial distance changes based on the eccentricity of the binary. And the red thing is the boundary of stability, and you see the 3 planets. Planet D is an optimistic habitable zone, but planet C is right in the middle of the habitable zone. Being super Earth, that could be a promising thing. Okay, next one. KOI 2939. This is another of those 2000 systems we were monitoring, and then we found something very interesting about this. Nothing for quite a while, and then we saw that little dip, right? So we took the features of the eclipsing of the binary away, and then we only look at that little dip over there. The light curve that you see shows primary eclipse being eclipsed and secondary being eclipsed and all that. But then here we remove all those and we only focus on the planet, and you see the dip caused by the planet. So we kept monitoring this, and we noticed that, oh, there is something very interesting. This shows the transit of primary and secondary. The light curve here, these 2 correspond to planet transit in secondary. And this one, that little piece over there, shows the planet transit in the primary. And if you take I'll show you the next slide, if you take the primary being transited by secondary away, that dip is more pronounced. So that caught our attention, and we tried to model it, and this was the only way that we could model that. So here's the thing. There is a time during the transit and during the eclipsing that both the planet and the secondary go in front of the primary. This is called syzygy, right? And then what happens is that during one during one epoch of observation, the planet keeps going around and around and around, and also transits the secondary star. We have two of these epochs, right? But what is interesting is that you only need one epoch to be able to detect the planet, and that is the last discovery we have made. This is Kepler 1647, and the paper is by Kostov et al. 2016. If you look at that, all the mathematics is there, that how you can detect a circumbinary planet in one epoch of observation if the planet goes in front of the primary and secondary in one observation, in one setting. This is how we are going to detect, hoping to use that method to detect circumbinary planets using test data. So this basically tells you about the syzygy and also the transit of the secondary and how the orbit is. That's the syzygy part and everything. That is after removing the eclipse of the primary by secondary, and this is only because of the planet. That is that. Sorry. And this is another. The discovery of this system was not only because of the technique that we used, important. It had also two other implications. First, the planet again is right in the middle of the habitable zone. But what is interesting about it is that if you go ahead and plot the location of the planet with respect to the boundary of stability, is much, much farther away. And also, this is the first planet that is Jupiter mass. Prior to that, those who were trying to model planet formation in circumbinary disk, they were saying that the circumbinary disk cannot form Jupiter mass planet, or Jupiter mass planet, they get scattered, they plunge into the star. So if you find anything, it will be only Saturn size. But some of us were saying that if planet formations in circumbinary disk are as efficient as on single stars, you've got to be able to find different type of planets. But the important point is where they are and where to look for. I will show you, I forgot to mention in those simulations for the disk, when we did the simulations of planet migration in the disk, we also carried out simulations for Jupiter mass planets, and we noticed that Jupiter mass planets have the tendency of plunging into the star unless you increase the viscosity to a certain amount and decrease the mass of the disk so you can stop them farther away. And this was the prediction came from our work on Kepler 34 and 38, and it was confirmed by discovery of 1647 that there are Jupiter-sized planets, Jupiter-mass planets in circumbinary orbits, but they are not going to be as close as the Saturn ones. They're going to be farther away. So this is the end of my talk. We have been studying circumbinary planets for many systems of many eclipsing binaries. As I said, we have many of them in the bag that we are going to announce within the next 2 years. We have studied them extensively, and the state of the theoretical work on them has matured up to a point that I can stand in front of you and with confidence say all these points. Circumbinary planets, that's supposed to be form. You see, that's what happens when you make your slides at 4 in the morning. Yeah. You shouldn't do that. So that is form. Circumbinary planets form at large distances in circumbinary disks. That is for sure. You can't form them close because of the interaction with the binary. In those regions, planet formation is similar to around single stars, and circumbinary planets most likely form as gas giants, because the same way that we believe, intuitively, we believe that farther away in our solar system, you form gas giants more efficiently than forming rocky planets. Planet-disk interaction causes circumbinary planets to migrate, and close to the binary dynamics is driven by min-motion resonances. Migration may stop only between resonances. If you get into resonance, you get scattered. If the disk has the property to stop you, you have no choice to stop between resonances. If you continue, like what happens with Jupiter mass planets, you plunge into the binary. Probability of stopping depends on the mass of the planet, and Jupiter mass planets have the lower probability of stopping, so if you want to stop it, they have to be farther away. Therefore, it existed, they are in large orbit. Episodically transiting and non-transiting planets are most frequent, and that is because of planet-planet interaction and interaction of planets with the resonances that put them on non-transiting orbits or episodically transiting orbits. I showed you a few cases of that. And circumbinary planets can exist on any orbit. The observed proximity of the orbits of a few circumbinary planets to the boundary of orbital stability does not have a physical basis. It is it's an observational effect. I'm going to stop here and take your questions. If there is any time, I can show you a few slides of S-types. Otherwise, we will have lunch. Thanks so much.
Okay, do we have some questions for Nader? Great.
What's the long-term stability of circumbinary planets? They survive long enough, for example, for this slide?
Oh yeah, so these that we have announced, they stay for billions of years.
TJ.
Kepler 34, I think you said you saw trans timing variations, but they were too small.
Yeah.
I'm not sure I follow that. So if they're too small, you're saying they weren't statistically significant?
No, I was trying to say that because they're too small, it's hard for us to model that and come up with the orbit and mass of the second planet. That's what you haven't done.
So you need a big signal to model something? I'm not following.
The
Is it
noise
clear?
doesn't let you. Yeah.
But it's for sure there.
Oh,
It's
yeah,
statistically
yeah,
significant,
yeah.
but then the signal's too
Oh yeah,
small.
absolutely. We see it, but it is damn hard to model that. So it's just hard.
Joanne?
So, how many, like two-part question, circumbinary planets, like definite detections, how many approximately?
Say again?
How many circumbinary planet positive detections approximately?
So far we have 11 of them that we have detected, and the ones that we haven't announced are about 6 more.
Okay,
Yeah.
so something like 20-ish. And then, how many of the eclipsing binaries do you have Kepler and or K2 data on? Like, what's the control sample, even though we know that they
2,000
probably
binaries,
Okay.
2,000 eclipsing binaries.
Okay.
Yeah.
And do you, this is like third party, for the circumbinary planets, do you see any metallicity
No, we don't.
different? It's just, plus it's a small size.
Let me say something about the connection between the 20 circumbinary planets and 2,000. You shouldn't draw any conclusion
Right.
there. The reason is that there may be many of them that are not transiting, and many of them that may transit, or they have transited before operation of Kepler, or may transit now that we don't see.
Yeah.
Now I got a question for you about the system you're talking about with the circum-eclipsing binary systems, where you said if you just saw a single event like that one, that would tell you everything you wanted to know.
Oh, that one? So, yes.
Well, you were just there.
Oh, okay.
Go back to the very end.
Yeah. Where do you want me to stop? Yeah. Next one.
You can just keep going back to the
Right.
beautiful images that I had in mind staring at. That was your overlay for your final slide.
Oh, that was the one.
Final slide.
There.
Going back there.
Okay.
There. Okay. So you say even if you just saw that kip data at that instant, that would tell you everything you want to know about the system?
You need to have, right, so this is a syzygy. As a matter of fact, Kepler 16 does have a syzygy. So this is one. You need one more transit of either the primary or secondary during the same epoch
By the planet.
by the planet.
Yeah, okay, that's what I was getting
Yeah.
at. So I thought you said at first you just
No,
saw
you-
that one time and you're done.
No, you need, yeah, that's the, so you need, in general, you need 3 transits to get the orbit, but you can reduce that to 2 if the
Okay.
planet goes through 2 of them, or through 1 of them. If this planet is here, it still works. Goes through 1 while the 2 are eclipsing, and go through either primary or secondary, during the same epoch. Then we can, yeah.
Okay,
Yeah.
gotcha. Larry?
Sorry, just a naive question. When you say epoch, do you mean like one rotation of the binary, or what does epoch mean? In
Okay,
this?
so for instance, for TESS, it means that you are observing one part of the sky for 27 days. That, yes.
Continuous stream
So
of data.
it's related
Yes.
to the operation of the spacecraft,
Yeah.
not the
No, that is
system
not.
itself.
No.
Okay, sorry.
Right.
Morris?
When shouldn't a binary system have planets? In other words, everything you've described says that there will be planets. It's just whether the luck of the draw is they're oriented for us to see. So do your calculations exclude or in any way show the negative sense?
Only when the binary separation is so large
That's what I'm getting at.
Yes, only if the binary separation are so large. If the binary separation are so large that the circumbinary disk becomes thin because its outer region interacts with passing stars and galactic tides, and the inner region, when interacting with the binary, gives you a very small annulus, then you may not have enough material to form planets. But those cases, they may have disk around one of these stars that could potentially form.
So then you have an S system.
Then you have an S system. The problem with those S systems is that we really don't know how to form them. They exist. We have about 6 or 7 of them in closed binaries, but we really don't know how to form them.
Erica, then Alicia?
So maybe I missed this in your examples, but can you have a circumbinary system where the planet transits one object but not the other one?
Yes,
Okay.
and
Is that in any of your 11 observed?
yes, 453, 413,
Okay.
those are all like that. Yeah.
So are you asserting that I cannot have a disk with any vertical or radial structure that will allow me to park a Jupiter mass planet in a close-in orbit, circumbinary orbit?
Listen, you're talking like a theorist. As a theorist, you can always cook up systems, you know.
Because you're depending on, I assume what's happening with migrating the Jupiter ones in faster is whatever torques are on the disk from the binary are
Right.
interacting with the torque
Right.
from the planet.
Right, so the part of the interaction between the planet and binary through the resonances, that really has nothing to do with the disk. That's celestial mechanics. So when your disk falls in that region, it is behaving. The gas doesn't see those resonances, but the particles and your planets will see it. And now, it's quite possible. Here's the thing: it's quite possible you can introduce so much gas to those regions close to the binary around the resonances that your planet can form them. You can actually damp the eccentricity of planetesimals and form them there. But once your gas goes away, then your planet becomes unstable.
No, I was asking more about how to stop the migration of a Jupiter mass.
Right. So we noticed that when you migrated, the stopping migration depends on the mass and the viscosity, mass of the planet, mass of the disk, and viscosity. Right. I'm not saying you can't cook up a model that stop the planet right there. But when we let the binary and disk interact with one another and we run many simulations, we just don't see that. What we see is more like this. Depending on the system, some systems can stop the planet, some cannot. But definitely, you can introduce so much mass and take a viscosity that do the job for you. But the question is how you can go from one system to another.
Paul?
Yeah, so wanted to talk about her. One of the things that's really struck me as very odd is normally dynamicists, when they're talking about resonances, those are the stable points, like in the solar system or around multiple planet systems around single stars. But in your talk, you pointed out that these are actually the unstable places, and
Right.
they cannot end up there.
Right. And actually, I can give you an example. I took that away last night from my extra slides, but I can mention that. Okay. Right, these are unstable because of the perturbation but the way that I can make this more intuitive is that just think about our solar system, think about Sun and Jupiter, right? Because of the perturbation of Jupiter, there are Kirkwood gaps in the asteroid belt, and they're all unstable. Right? Now, just visualize. I bring Jupiter in. As I bring in, some of the unstable Kirkwood gaps goes behind it, some of it stay in front of it, and when I bring Jupiter very close to the Sun, all those Kirkwood gaps will be behind. So this is very much similar to what we see in our solar system, where because of the effect of two massive bodies, resonances become unstable. Now, your resonances may become stable if you have, for instance, two planets getting into resonance with one another. But here you have two big massive bodies that make the orbit of the planet unstable. I took that. I always leave that. So the reason is that I give this talk to students, and I say, okay, if you can say what is the equivalent of this in solar system, I'll buy you a pizza. And so I took that away.
Preston?
Out of the 20 you mentioned, how many of them are walking planets?
Only the last one that I showed. All the other Saturn size or Jupiter size. So. Only this one is at the range of super Earth. Whether it is rocky or not, I cannot tell. But I can tell you the mass is 2 to 5 Earth mass.
Yeah, but the density is really low though.
Correct. So, none. Yeah.
Is mass from RV or from transit time?
From transit time. We don't have a RV. No, we don't have RV on Eminence.
Is it possible to get?
No, is it possible to get, Paul? I don't think so.
How bright are these things? It's going to be really rough.
Yeah. I don't think so.
Okay, if there are no further questions, let's thank Nader again.
You continue the thread. There's something here.
Yeah, I mean,
You're back. How was it?
Well, one of the first